Hello, good evening to everybody. We'd like to thank all of you that are here and will assist these webinars, dialogue webinars. And first of all, we'd like to thank our sponsors, FAPERJ, Analytica, Thanks, e Thermo Fishers, for the financial support. And all the group that work hard to have you all here, assisting the presentation of our colleague, Professor Leandro. I hope that all of you enjoyed the presentation. You may have many questions and delight with the new knowledge that we will assist. Also, it's a pleasure, so you can stay here. I'd like to introduce you, Professor Leandro, and the professor is Bachelor in Chemistry and Doctor of Science in Chemistry at Campinas University in Brazil, with University of Toledo, United States, a sandwich period. He's a professor at UNICAMP since 2017, and he has many projects, and some with Petrobras regarding machine learning and chromatography in the acid composition study in petroleum. He also has many awards, example given in 2018. He is in the Power List Top 40 Under 40, the analytical scientist, and he has already 44 published papers. He is also research at CNPq. He has many students, undergraduate and postgraduate students. His research includes all aspects of gas chromatography, including sample preparation, multidimensional separation, and process strategies for large GC-MS data. So, Professor Leandro Wang, you have the word is all ours. Thank you for accepting our invitation.
Thank you, Dr. Azevedo. I'm glad to be here. So I'm gonna share my screen and hope that everything goes right. Okay, so thank you for the kind invitation. And in this seminar, I would like to share our first impressions on the FT-Orbitrap GC system for targeted and untargeted petroleomics. So Leandro, if you're having a hard time spelling my name, you can just call me Leo. So I teach chemistry at the University of Campinas, and these are the co-authors that helped make this, put this work together. So first and foremost, again, I would like to thank the organizing committee and sponsors. I would also like to acknowledge and thank all my students and research collaborators for supporting our work. So thank you very much. So the outline, we're going to briefly discuss the contemporary challenges or analytical challenges that we may find in petroleum industry. But most importantly, we want to define the scope of the analytical methods so that we can determine what is the scope that we need to solve or to answer the question that we're looking to solve, in fact. And by doing so, we're going to come across gas chromatography coupled with high resolution, accurate mass spectrometry, and comprehensive two-dimensional gas chromatography also coupled with mass spectrometry. And in each of them, I guess we're going to showcase some case studies and discuss, how far can we go and what are the qualitative results that we can achieve from each platform. Now, when we look at instrumental analyses, we really perceive that there's a continuous shift on the way that we look at instrumental analyses when we look at analytical chemistry, right? Because the scope is actually expanding. We're moving from purely QA and QC techniques into platforms to explore or mine chemical information. So basically, we're seeing much more research opportunities for untargeted analyses. And what this means is that now the goal is to gather as much information from your complex sample as possible. And there are many things that we can tackle, many problems that we can tackle in petroleum industry. One example that I find it very interesting is to understand how emotions work, which compounds help stabilize the emotions, which compounds modulate the viscoelastic properties of water, oil, emulsions. So this is the kind of question that we can answer using instrumental methods like mass spectrometry, for instance. So it essentially allows us to gather information at the molecular level to improve our understanding about complex processes in petroleum industry. So in this case, we're looking at emulsion stability. Now, another group of applications that I think that are very interesting, and we're likely going to see much more of them coming up, is the application of data science to improve business intelligence. So you can look at petroleum industry and you may find yourself performing multiple experiments to determine multiple properties. And I guess our goal would be to have a single instrumental measurement, and from this single measurement be able to predict multiple multiple parameters or properties from your sample. So I'm highlighting this paper from Synovac's group, where they're basically performing predictive modeling using partial least squares regression. And you're basically predicting hydrogen content, heat of combustion, viscosity, all from a single chromatogram. So I think these are the kinds of research opportunities that we're very, very eager to see being published in the recent future or the near future. Now, when we look at qualitative analyses, we have basically different depths, meaning that you can have a more superficial and fast method, which aims at fingerprinting, and you can do fingerprinting using mass spectrometry. You can use it, perform it doing NMR and infrared spectroscopy. You may want to have a more detailed composition or information about the composition of your sample. So then you may be targeting group type analyses, which we're showing here. So it basically gives you an overview of the composition of your complex sample. So you have, mainly the information about the classes. So you may have the hydrocarbons, oxygen containing, so O class, O2, which you may have acids, nitrogen containing, sulfur containing, and so forth. And then you can have a more detailed analysis, which is the individual identification. So we basically want to know which isomers are the features for a specific property. Now, when we come down to the isomer analyses, we basically find that there is a resolution difficulty, meaning that it is easier to resolve constitutional isomers. They're actually more easier to resolve than diastereomers, and then followed by enantiometers. So this is the kind of the scope for qualitative analyses. And what you're going to do with each of these approaches depends on the answer and research that you're looking for. Now, when we think of the traditional workflow that we typically employ for gas chromatography coupled to or hyphenated to mass spectrometry for group type analyses, right? We're basically looking at we start from the chromatogram. So you basically want to pre-process the chromatogram. So you're going to correct the baseline. You're going to correct for small rotation time shifts, if there are any. You may look at peak identification, which is usually assisted by mass library searches, retention indexes, and you may also use additional features such as template matching. And then you're going to generate your peak table, which comprises of the peak number so that you can locate it in the chromatogram, the isomer identity, and the peak areas, essentially. So this kind of approach, it's more common when we're looking at mass spectrometers that exhibit unitary resolution, so basically quadrupoles and low resolution time-of-flight mass spectrometers, and electron ionization, just because you're performing mass spectral library searches, right? So after you generate your peak table, you're basically going to compile the data across all your samples or classes or groups of samples, and you're going to report it. So this is one of the paths to achieve group type analysis using GC-MS-based platforms. Now, what we wanted to showcase is that as far as chromatography is concerned, I think there's a lot of opportunities that we can learn from petroleomics that typically explore high resolution and accurate mass measurements. So when you have a GC-MS, wherein your MS system exhibits high resolution and accurate mass, you can actually pre-process your data. So meaning we're going to have a background removal step. You're basically going to perform the elemental composition assignment, followed by peak integration using the extracted ion chromatograms. Now, I need to highlight that this can be performed manually, but there are dedicated software so that you can perform this in a more automated fashion. So basically what you have, one example is you're going to have your chromatogram. So for each of these, so for each peak in your chromatogram, you're going to have mass spectra. In this mass spectra, when we're working with high mass accuracy and soft ionization, so in this case, we're working with chemical ionization, you're basically going to have your adduct ion, right? So no matter the compound, you're going to have your adduct ion, unlike electron ionization, where you can't always detect the molecular ion. So this makes compositional analysis much more trustworthy. So we basically have our data. We're going to perform all these steps. So basically background removal, you're going to define the ion type, if it's an odd or even electron. Assignment criteria, so basically mass error threshold and confirmation using the fine isotopic pattern. And stepwise assignment, response factors, if you want to perform quantitative analyses, and seed formulas. Seed formulas are particularly useful when you have some preliminary knowledge about your sample. So you can feed molecular formulas that you know that are present in your sample. And this is going to give you a peak table or a qualitative table more precisely. So you're going to have amongst many information, you're going to have your accurate mass, the formula that you achieved by these assignment criteria, and the area for the extracted ion chromatogram. Now, I need to highlight that this area is actually determined for all the isomers of a particular formula. So we're not looking at distinguishing the isomers. We're just performing group type analyses. Now, this is just a step. The next step, obviously, is to compile the data across all your samples and report the data. So this is one way to achieve group type analyses. Now, what I like about this approach using the high mass accuracy is that it is somewhat less subjective to start, just because you don't have to rely so much on template matching, which is the aforementioned approach. So likely this is going to give you a more robust group type identification. Okay, so now that we've defined the workflow for the accurate mass measurements, I would like to briefly illustrate how the instrument works. Now, just because I'm assuming that many of the audience comes from a GC-MS using quadrupole and time-of-flight mass spectrometers background, it may be sometimes, I guess, new, the Orbitrap technology. So just in brief, so this is a schematic of the hybrid Q executive system. So we basically have the ion source, all the transfer lenses, so that you're removing the neutral molecules. But essentially, we have a quadrupole here, a C-trap, the Orbitrap mass analyzer, and a HCD cell. And in the back of the HCD cell, we have a collector. So when we look at this hybrid mass spectrometer, we're basically, throughout the seminar, we're performing full MS data acquisition, meaning that we're acquiring the mass spectrum over a large M/Z range. So when you're setting up the method, the quadrupole is going to determine the mass to charge ratio range of the method. So what it does is basically it acts as a broadband mass filter. So for instance, I can say that we want to acquire the spectra over starting from 50 to 500. So across the time, it's gonna, the ions with M/Z anywhere between 50 to 500 are going to have a stable trajectory across the quadrupole, and they're going to reach the C-trap. So what I mean is that the quadrupole is not scanning. It does not scan in the full MS data acquisition mode, unlike QMS systems where you're actually scanning, right, to perform full MS data. So this is the role of the quadrupole transmission. Now, when we look at the mass analyzer, we quickly realize that it is a bit orthogonal from what we're used to, meaning that the mass spectrometer is designed to handle much more efficiently the ions being generated. So we're not getting only mass resolving power, but we're also achieving detection limits and sensitivities that are unprecedented for full mass data acquisition. So this is one cycle, one full mass cycle, and then you're going to have multiple cycles across your GC run. But basically, we have the automatic gain control scan or pre-scan, the AGC scan. What happens is that we're going to estimate the ion current using the collector in the back of the HCD cell. And this estimate of the ion current allows us to determine how many ions you want to store in the C-trap. So in our case studies, we're basically working up to 3 million ions inside the C-trap. So the C-trap basically is going to store the ions while the Orbitrap is performing ion detection or your image current detection. So in these two time bars, we're basically showing that the C-trap is collecting the ions and is performing the collisional cooling of the ions. And once it fills up or it reaches the maximum injection time, you're going to send this pack of ions into your Orbitrap mass analyzer, and you're going to start the image current detection, followed by the Fourier transform and processing. So this is basically how it works. So while the mass analyzer, while the Orbitrap is performing detection, you actually have the C-trap storing the ions. So this gives you a much more efficient ion management, and it allows us to get to achieve very low detection limits, even using full mass acquisition mode. So this is just to feature the Orbitrap, and the image current detection relies basically on the axial resonance of your package of ions, right? So as your package of ions is oscillating across the central electrode, it is going to induce a current on this side or this side, which is basically how you're going to generate your image current. So as you have multiple, a package of ions with multiple M/Z values, you're basically going to get this kind of sinusoidal wave. And when you apply the FT transform, you're actually able to deconvolute and find the individual contributions for each M over Z. So this is kind of the idea. One of the main things that I wanted to highlight is that when you're performing image current detection, the response factor is proportional to the charge of the ion only, unlike the electron multipliers and MCPs, wherein the mass also affects the response factor of your signal. And unlike direct ion detection, like the electron multipliers and the MCPs, when you have indirect ion detection, you really don't need to replace your detection system just because it's indirect detection. Now, when we look at, obviously, when we look at the mass resolving power of the Orbitrap system, it depends on the curvature of or the magnitude of the DC field that you're applying inside the mass analyzer, but it also depends on the transient values in which you're measuring the ion current. So naturally, if you want to have higher mass resolving power, the transient values are going to be quite a bit longer. But this doesn't necessarily mean that you can couple it to chromatography. So the first case study, we're looking at a diesel biodiesel sample, diesel biodiesel sample, and we're performing group type analyses. So this is the settings that we're using. So basically the injection time is set to automatic, and we're using a mass resolving power of 120,000. And in this case, we're using log mass, and we're using as the reference ions the column bleed from our PDMS column. So this actually gives us only about 2.5 to 3 spectra per second. So it's a bit slower when you're using log mass. If you turn off log mass, it goes much higher than 3. You can get even 4 spectra per second at 120,000 mass resolving power. And we're using chemical ionization in the positive mode. So in this case, we're still using methane at 1.5 mil per minute. So this is the chromatogram of our sample. We can see the peaks from the hydrocarbons eluting in the beginning of the chromatogram. And towards the end, we have the peaks from the methyl esters, which actually compose the biodiesel portion. So when we look at the mass accuracy for over 50 successful assignments, when we have the log mass option on, the maximum mass error that we get is about 1 ppm. But without the log mass, you can actually see up to 5 ppm mass errors when you're assigning the identities for your peaks. Now, when we set in the method for 120,000 mass resolving power, it actually gives you about 120, 130 mass resolving power for M over Z 200. But as you're decreasing the ion mass, you actually get higher resolving powers. So when you're looking around anywhere between 60 and 70, you're going to get over 200,000 mass resolving power. And this is fairly interesting because at this very end, around 63, you're going to have the dimethyl sulfide. So you're getting more than 200,000 mass resolving power for these analytes. And in the larger mass to charge ratio, you're going to get anywhere around or above 80,000 mass resolving power. So this is how the Orbitrap system behaves. And I'm highlighting this because depending on the sample that you're working with, and you may want to adjust the mass resolving power according to the critical pair, right? So for instance, the worst case scenario would be a mass difference between this isobaric cluster of only 3.4 millidaltons, which would require anywhere over 60,000 mass resolving power to perform or to resolve or to acquire your fine isotopic pattern. And we need the fine isotopic pattern because we use it to confirm the assignment, the elemental composition assignments when we're basing the group type analysis on your accurate mass measurements. Now, If you have good chromatography or somewhat good chromatography, this will certainly reduce peak overlap. And by reducing peak overlap in your GC run, you actually alleviate the demand for high mass resolving power. So you can actually get the same results with a bit less mass resolving power. But naturally, you need to look at every case. Okay, so as far as the peak reconstruction is concerned, we're looking at the total ion, and we're also looking at 2 extracted ion chromatograms with a 5 ppm window. And what we see is that even with the 120,000 mass RP setting, we get at least 20 spectra across the peak. And you need at least 18 spectra across the peak for proper reconstruction of the peak, thinking about quantitative analysis, but also because you need anything above 18 points per peak to perform deconvolution. So we're hitting the mark of 24 to 30 spectra per peak. Obviously, this is a more intense peak, so it's going to be a bit broader. So you're going to get more points across the peak. This is a low intensity peak, and you're getting about 24 spectra across the peak, which suffices for gas chromatography. Now, when we look at the automated stepwise, when we look at the automated elemental assignment of the elemental composition, we need to be very careful because small molecule analysis is not trivial. So if you look at the PubChem database, you actually realize that you have the most entries in the small molecule region. So what this means is that if you try to assign all these elements simultaneously, knowing that these elements will have different Kendrick mass defects, like hydrogen and carbon have a positive mass defect, while these guys have a negative mass defect, you can assign basically a formula to your monoisotopic mass, and this doesn't mean that you're assigning the correct formula. It just means that you're beating the numbers just because you have positive and negative values. So it is very important to determine how you're going to assign the elemental composition. And this is done in a stepwise manner. So we basically set the mass threshold, the mass error threshold. We typically want to work with anywhere below 5 parts per million, and this is how we determine it. And the stepwise assignment is based on preliminary knowledge about the samples. So the workflow for GC-based petroleomics is not the same workflow for electrospray ionization petroleomics, which is naturally very different from food analysis and metabolomics. So in this case, when we think of the scope of gas chromatography hyphenated to mass spectrometry, and we want to apply the following passes or steps for the assignment of the elemental composition. So we first off, we start to assign the hydrocarbons, followed by the oxygen-containing, nitrogen-containing, sulfur-containing, and then the residual mass spectra. In the residual mass spectra, you're assigning compounds that will have oxygen, nitrogen, and sulfur. So what this does is that it avoids unreasonable identifications that will eventually meet the mass error criteria. And it also means that now more than ever, we need fine isotopic pattern confirmation, right? You can't assign a elemental composition without confirming it with the fine isotope pattern. Now, what this generates is a qualitative table. In this case, we'll have a column for the class, a second column for the double bond equivalent, formula, accurate mass, so basically monoisotopic mass, the errors, and all the statistics that comes across with it. But it basically, for this diesel sample, you generate around over 500 entries of successfully assigned elemental compositions. So this is group type analysis using high mass accuracy based experiments. Now, what is interesting when you have a chromatography step in your method is that you're actually able to plot the extracted ion chromatograms with a 5 ppm window for each of these entries in your qualitative table. And this shows you basically how many isomers are available in your chromatogram. Now, when we look at these molecular formulas, it becomes this highlights the need that we need to go beyond soft ionization in order to determine which of these isomers we're referring to, which isomers we're measuring. So we need ion fragmentation information to elucidate the individual structures of each of these isomers, and we need retention index to determine, just to assign the position across your chromatogram and thus build a reliable database. And naturally, when you the more peak overlap we have, eventually it may hinder some or the identification of some isomers. So we still need chromatographic resolution even when using a powerful mass spectrometer in the GC scope, naturally. Now, when we look at the unresolved complex mixture, it becomes, even know that we're working with diesel, and diesel is a cut of petroleum, just like kerosene, naphtha, you'll always get the UCM profile. And this is great because we advertise gas chromatography and comprehensive two-dimensional gas chromatography based on the UCM profile, right? But it is expected and predicted by the Bodinsky continuity concept. And so when you think of a same value for the boiling point, or even the elution temperature using a 100% PMS column, you'll notice that you'll have a distribution on your carbon number of the compounds that are colluting. And this happens because for the same boiling point or elution temperature, as you're increasing aromaticity, or when you're adding heteroatoms like oxygen, nitrogen, or sulfur, you're actually decreasing the carbon number. So that means that part of the UCM, when you fix a elution temperature, you actually have a fairly like 2 to 3 carbon number distribution, and this happens because of these observations. Now, the qualitative table, you can visualize the data in many ways, and one of the ways involve the double bond equivalent. So just to showcase how we determine the double bond equivalent, or DBE value, we basically take into consideration the number of bonds that each element can undergo. So you determine the factor per atom. So for instance, a straight chain hydrocarbon will have a DBE value of 0. When you have a cyclic compound, you have a DBE of 1. So for this naphthenic acid, you have a DBE of 2, just because you have the cycle and saturation here. And for benzene, you have a DBE of 4. So you basically have the cycle and 3 double bonds. Now, when we look at when you plot the carbon number versus DBE value, we actually notice that there is a distribution of our assignments across this space, and you can define this space as the maltine composition space. Obviously, for this sample in particular, we're missing the short hydrocarbons and these hydrocarbons over here. But this is fairly certain that this is the maltine composition space. And as you're increasing the carbon number, you're also increasing the boiling point of the compound. And when we think of the same boiling point number, as you're increasing aromaticity, you actually notice a decrease of your carbon number. So I took the liberty just to set this to showcase how you're increasing aromaticity and you're decreasing carbon number for compounds with the same boiling point number. Now, in this case in particular, it's not the instrument's fault that we're not seeing the some of the hydrocarbons. I actually took the sample, which was which consisted of a urea adduct. So we're basically removing the N-alkanes from our samples, and that's why you don't see the N-alkanes in bottom. And likely we're taking some alkenes as well. So this explains why we're missing so many hydrocarbons, and I apologize for this. I only realized later this afternoon. But another way to visualize the data, aside from the carbon number and DBE plot, you can plot the Kendrick mass defect over the Kendrick mass. And what this will give you is that it kind of showcases homolog series. So you can filter out by the Kendrick mass defect, or you can look at certain Kendrick mass, and then you quickly realize that your saturated hydrocarbons are going to be on the bottom, or the more saturated. And as you're increasing the aromaticity, you're actually going up the series. So this is one way to visualize the data, which is by plotting the mass defect. Now, we wanted to showcase a study that benefits from group type separation, but also evaluates how low can we go. I mean, using full MS, what is the detection limit that we can get for a specific compound or for a group of compounds? So we decided to study naphthenic acids using the GC-Orbitrap system. And for the sample preparation, we're working with hollow fiber liquid phase microextraction, which is a way to perform liquid-liquid microextraction, but we're doing it in a microextraction scale. So what we're doing is we're using isooctane as the extracting phase. The donor phase is a real world sample. And for the GC-MS system, we're basically using a PDMS column, chemical ionization, and 100,000 mass resolving power with these settings. Now, we had a couple samples, but so these are two samples. I forgot to name them. I apologize for this. So the sample on your left is the technical mixture from Sigma Aldrich. So this is the total ion chromatogram. And on your right, on the right side of your screen, you have a real-world sample wherein we analyzed everything using hollow fiber liquid phase microextraction. So when we apply the automated workflow and look at the class distribution for our group type analyses, we realize that the O2 class, or the naphthenic acids, are actually the most abundant class in our sample, followed by the hydrocarbons. Naturally, when you're working with a real sample, you'll have more classes that you didn't expect to see compared to your standard, just because it is a real sample. Now, if we take a closer look at the naphthenic acids, so now we have our carbon number over DBE plot, we quickly realized that the real sample actually had more naphthenic acids than the technical mixture. And we wanted to highlight three groups within the O2 class. So the first one is the compounds or the series with a DBE value of 1. So you basically have your straight chain acids, organic acids. You may have branched as well. So for a DBE value of 2, you have your these naphthenic acids, basically, either with a 5-member ring or a 6-member ring. And we wanted to highlight the series, the smaller series with a DBE value of 4, which are actually the adamantane acids. So this is very interesting for us. Now, we wanted to see what are the levels that we're measuring and how low can we go? I mean, what is a minimal concentration that the compound needs to be found so that we can actually pick it up when performing group type analyses? So we basically took the C7 naphthenic acid and we performed a semi-validation. So what we found is that the limit of detection and limit of quantitation for the instrument was actually 0.1 parts per billion. So this is the detection limit for the instrument operating in full MS mode. And this is actually very, very surprising. It's about the same detection limits as we have for a standard triple quadruple GC-MS system. So we were very happy with that, just because we're working with full MS. So you're not, you don't have to program all those transitions, the PRMs, in order to get the sensitivity that we need. And obviously, when you're not programming the transitions, if you have some retention time shift, you don't have to shift your transition windows. So this was very, very exciting for us. For the detection and quantitation limit of the method, just because we're working with a microextraction technique and you get a favorable phase ratio, we were able to drop down to 10 femtograms per liter for our limits. So this is just some numbers for our analytical curve. And basically, accuracy anywhere between 90 to 97%, depending on the concentration, and precision anywhere from 3 to 13%, also depending on the concentration. So, you know, we can actually see a lot from this, from these experiments. So visually, just to showcase, this is 0.1 ppms of our standard in diesel. So this is the total ion chromatogram, and this is our analyte peak, the adduct ion. So we're able to integrate this and achieve the limits that we reported in the previous slide. And we're looking now at the adamantane carboxylic acids. So this is the total ion chromatogram of our water sample, and these are the isomers for three members of the series of adamantane acids. So we have the C11, C12, and C13. And what becomes clear is that we can successfully assign the elemental composition, but we're still far from knowing which isomers are found in our sample and how they are distributed. So this information may be very important depending on the question that you want to ask your samples. So we obviously need to improve the chromatography of the isomers. Now, when we look at complex samples, we bump into the peak capacity problem. And the peak capacity problem states that a complex sample will typically exhibit an overwhelming number of components with a broad distribution of physical and chemical properties. So it makes resolution very difficult. So you expect to have some peak overlap. So in order to tackle the peak capacity problem, we have hyphenated methods within gas chromatography. And one of them is comprehensive two-dimensional gas chromatography, also known as GC by GC, which you already had a webinar recently. Now, when we have a composite system that exhibits a unprecedented peak capacity, the analyst is able to attain a more pure spectrum compared to conventional 1D GC analyses, but it also allows for better peak integration. So this is very good on a quality and quantitative aspect. And this is shown in this chromatogram. So I'm showing a flow modulated GC by GC QMS system. So this is a single transmission quadrupole. And you can basically see that the compounds that are in the same vertical line are typically colluding in your primary column or first dimension. But naturally, there are many instrument configurations available. And what I wanted to highlight is that for our case in the university, we are typically looking for a instrument setting that allows for low operational expenditures, meaning that you don't have to spend much money in order to keep the instrument running every day for as many weeks as you need all the time for routine analyses. But also you need long-term stability. If we're thinking about assembling a database, which makes your study much more valuable, then you need long-term stability. And the long-term stability is not just about the mass stability, the signal stability, but you're also looking at retention stability, which implies that you need reproducible modulation. So there are many ways to achieve this, but I wanted to highlight flow modulation. I really think that this is a very interesting alternative. So obviously, flow modulation does not exhibit the same peak capacity as cryogenic systems, but you do have very, very interesting OPEX values, and you get great peak capacity. Obviously not the same as cryogenic interfaces, but still it's a vast improvement. Now, when we look at flow modulation, we basically come across the two most popular forms of flow modulation. The first one is the forward fuel flush flow modulation, which was first described by John Seeley's group. So this is the setting. You can use basically two base plates, like a 3-port base plates in order to assemble the setting. And you have the reverse fuel flush, where this is the setting that you'll need. So when we look at these two configurations to perform flow modulation, we need to highlight the dynamic range problem. And this happens when in your sample, you have peaks that are found in very high intensities and peaks that are found in very low intensities. So what this means is that usually it may be hard to find a single method that is able to generate a good separation for all peaks, high and low intensity peaks. So when we look at these two methods for flow modulation, we quickly we can realize that the reverse fuel flow operating mode that actually gives you a better modulation, better chromatography when you have the dynamic range problem. So once we've set the reverse fuel flush configuration as our standard configuration for the next case studies, we wanted to tackle the general elution problem, meaning that when you look at flow modulation, so we have the forward fuel flush, and we have reverse fuel flush using 3 geometries for your bleed capillary or restrictor capillary. We need to realize that in flow modulation, because you have an additional source of carrier gas, which is also called the auxiliary gas, you're reducing the pressure drop across the primary column, across your first dimension. And when you reduce the pressure drop across your primary column, what you're doing fundamentally is improving retention, but you're having excessive retention, which leads to higher elution temperatures. And these higher elution temperatures, what they do is that they restrict the molecular coverage of your GC method. So when we think of petroleum analysis or petroleum industry, it is very important to have a method that is able to tackle extremes. You want to be able to analyze C1, C2, but you would also like to have the same instrument analyzing C40 and above. So what this means is that we need to understand what is influencing the pressure drop when we're performing flow modulation. And we could quickly realize that by using the reverse fuel flush and by reducing the impedance of your bleed capillary, you're actually increasing the pressure drop across your primary column and therefore allowing to elute a broader range of compounds, so a broader volatility range, considering a maximum operating temperature of 280, which we are simulating a polyethylene glycol-based column. Now, when you change the impedance of your bleed capillary, you're also changing the differential flow conditions for flow modulation. So differential flow basically means that when you're reinjecting or when you're sampling the bands in your modulator, you have different average carrier gas flow rates, right? So what it does when you're changing the impedance of your bleed capillary, you're also going to be affecting the carrier gas flow rates, and naturally you may impact the duty cycle. You may actually lose compounds from your sampling loop just because you're not having a very a differential range for your fill and flush stages. So what we wanted to do was to find the optimal conditions to maintain the duty cycle. Basically, we don't want to lose compounds during modulation, so we wanted to set the duty cycle as high as possible. So we realized that for this bleed capillary, you can work with up to 6 seconds modulation period with a reinjection pulse of 400 milliseconds. And this was done by, this plot was done by monitoring the profile from the second dimension and the bleed capillary. Now, now that we've defined that we're working with reverse fill flush and we have our column set and our bleed capillary, we can analyze two extremes, or almost two extremes. So in the upper chromatogram, we have naphtha, which exhibits a boiling point range anywhere from 15 to 150 degrees C, and diesel, 150 degrees C up to 403 degrees C for your boiling point range distribution. And what we see is that we actually use the same instrument configuration, same columns, same bleed capillary. We just adjusted the temperature programming of the GC oven. So this showed us that, and we realized later on by using the instrument routinely, is that flow modulation, if carefully optimized, can withstand a very broad range of volatility. But the actual limiting factor is the column's thermal stability, or maximum operating temperature and phase ratios. So in order to perform the GC by GC experiments, just because we have narrow peaks across your analyses, we also need to improve the data acquisition settings for the mass spectrometer. So in order to do so in the Q-Executive system, we reduced the mass resolving power down to 15,000. We're not using lock mass. And we've switched to electron ionization just because we wanted to take advantage of the mass spectral library searches. Now, when you set the RP setting to 15,000, we actually get almost 30,000 mass resolving power for this low mass range, anywhere between 50 to 70. And over here, you get 22, 20, up to 13,000, around 350. So we'll see how it goes. So using this setting, and this is just to kind of illustrate from where we started. So this was back in 2017. This was our first setup for flow modulation. So basically, you need a auxiliary pressure controller for your auxiliary gas. And in the back, we have the TTL readings from the gas chromatograph in order to synchronize the modulation. A Arduino microcontroller, which is the poor man's modulator, and a solid-state relay just to control this valve. And we were putting together the modulator using these pieces either from Balco or Trajan. But it's still a very neat interface, in my opinion. So now we have this chromatogram of diesel, and I just wanted to illustrate the 23 hertz or 23 spectra per second. So across this peak, you basically get around 29 spectra across the peak. And for this peak, we actually get 26 spectra across the peak, which is also sufficient for peak reconstruction. And it is also sufficient to start deconvolution. So we're actually acquiring now the mass spectra using the centroid mode. We switched to centroid and not profile anymore. So this is the molecular ion for this guy, and this is the molecular ion for this other peak, so peaks number 1 and 2. The mass error, even though we turned off lock mass, is still relatively low, and you're able to assign the elemental composition, and also from the elemental composition, you can determine the double bond equivalent. So we can visualize this data using the carbon number versus DBE plot, and we actually found that the same resources are available to us when performing GC by GC compared to conventional 1D GC analyses, even though we've reduced the mass resolving power down to 15,000. We still have very good, we still have reliable assignments. And there's obviously different ways to visualize your data as well, such as the Van Crevelen plots. So I wanted to showcase what it looks like when we improve chromatographic resolution with accurate mass. So we have our qualitative table that was compiled from the accurate mass measurements. And now we're using each of those entries to generate the extracted ion chromatograms with a 5 ppm window. So this is anthracene C15H12. We can basically see the roughly 4 isomers over here. So I'm hiding the elution window. So this is where you're going to find. So we basically can't see it on the total ion chromatogram just because of the color scale. But when you extract the ions, it is very clear, much easier to perform the detection. And I do apologize for the GC by GC users. I had to use a very unusual phase shift for the total ion chromatogram, just because I wanted the extracted ion chromatograms to look nice. So because these guys, some of them were out of phase, they were wrapped around. So I chose the phase shift to prioritize these guys and not the total ion chromatogram. So I apologize in advance. So these are the isomers for anthracene, and these are the isomers for the NO2 class, which was surprising to find. I didn't know of them in diesel, so I was very excited to see how we can explore the high mass accuracy in GC by GC. So in this case, in our case, it actually generated more questions because we found unexpected elemental assignments such as NO2. I didn't realize that there were so many peaks for this class, which is a good thing. Naturally, it is more information so that you can build your models for predictive modeling. And it raises awareness to, so we try to identify these guys, and some of them are just very hard to identify. And my feeling is that they're hard to identify just because we may be these are very unusual compounds, so they're probably not reported in mass libraries. So this process highlights the importance of having a reliable database for mass fragmentation, for mass spectra. And it opens opportunities for in silico modeling. I think this in silico modeling may help you guide the identification of the individual processes, because once you understand one elution pattern of a group, you can use some assumptions to guide in the following. So this is very good about GC by GC. And lastly, we still need to confirm at least a few of the homologues in the series using standards. So having said this, we're very excited to have our research collaborators. So this is the Drewberg group. It's a organic synthesis group. So basically what we plan on doing is highlighting a potential structures, and they'll synthesize it, and then we'll confirm the identification. So having said this, I would thank again the organizing committee, the sponsors, and everyone that is attending this webinar. And if you're liking the content of Alago, please smash the like button and subscribe to the channel. So thank you very much. I think you might be muted.
Yeah, sorry. Again, no one advised me. And thank you, Leandro, for your great presentation. And let's go to the questions. The first one was from Vinicius Pereira from Federal University of Rio de Janeiro. And the question is, how much of the minor analytes is lost during, flow modulation combined with a resolution mass spectrometry at resolution of 120,000. How is the sensitivity of the technique? Did you understand?
Yes. So that is a very good question. So if we do have any losses, it's not due to flow modulation. It may be because by reducing the resolving power, we may be missing the assignments. But so far, we haven't seen a loss in the assignment capacity just because we've shifted from 100,000 mass resolution down to 20,000 mass resolution, but we've improved chromatography significantly. So right now, we haven't seen the difference, but this is fairly recent. So this data is from this year, and anything can happen. So, but for now, we haven't seen the difference. As far as the sensitivity is concerned, some mass analyzers, when you change the mass resolving power, you may lose sensitivity. So you have high sensitivity mode, high resolution mode. It happens just because of specific mass analyzers. But in this case, mass resolving power of the FT-Orbitrap does not influence the detection limits.
Okay, and let's go to the second question from Gutierrez dos Santos from Federal University of Rio de Janeiro. Great presentation. My first question is about the processing steps. Are they most useful for analysis by APACI? Do you indicate them for another ionization mode, example given electron spray?
Hi, Gutierrez, that's a very good question. I am fairly new to this petroleomics field, but what I realize is that if you have if you need to perform group type analyses and you're generating your ATAC ion independently, if it is chemical ionization or APCI or ESI, the workflow is very, very similar. I believe that many of us use the same software. We're using Composer to perform elemental assignments. So it's the same pre-processing steps. Obviously, the details might change, but they're fairly the same.
Another question from Gutierrez is, what is the effect of S-lens frequency on Naphthenic acid analysis?
I'm not sure I understand the question, because the S-lens is just after the ion source. So what it does is that it removes the neutral compounds that weren't ionized.
The question may have some, for example, if you have tried any difference from the value that you put in the S-lens frequency, and how this may affect the analysis of naphthenic acids. I think is that.
Right. Thank you for clarifying. We haven't tried changing the frequency of the S-lens. even in the advanced mode in the RQ Executive GC system, it wasn't available as far as we know. Maybe for other Orbitrap models, it may be. So I don't know how to answer this question at this moment. I apologize.
No problem at all. That's good. Another question from Vinicius is, I would like to know if peak obtained by GC-Orbitrap high resolution mass spectrometry is large enough to perform fragmentation experiments that may be needed for geochemical biomarkers assessment.
Hi, Vinicius. That is an excellent question. It is possible. The peaks are wide enough. They're basically 5 seconds, 6 seconds wide peaks. So you can perform PRM experiments by selecting a precursor ion from your target list, from your global list, or you can perform data-dependent experiments. So the way to engage in these experiments is that you may want to set the mass resolving power down to 60,000 for the full mass setting. And since you're going to be performing data-dependent experiments, then you can set a mass resolving power of 15,000. So that will allow to perform the MS experiments, but at a much faster rate without losing information in the full MS setting. But obviously, there is a limit to how many data-dependent experiments that you'll be performing. I find that 3 to 5 is sufficient for gas chromatography. If you extend this top end, you'll spend too much time fragmenting, and you start losing information when you're performing full mass mode.
Okay. Now from Tamara Barra, from Federal University of Rio de Janeiro. Resolution and structure elucidation of unknown small molecules by mass spectrum are not a trivial task, as you mentioned. Could you suggest something to improve it?
Well, that is the gold question, Tamara. This is what we're trying to figure out. There isn't a strict method for this already. There are multiple routes, I guess. In silico modeling, having a really good background or on organic chemistry to understand the fragmentation mechanisms. GC by GC certainly helps because you have the structure of the chromatogram. So if you figure out some elution patterns, it just helps you to infer some structural information about your peaks. But I don't have a general rule. I do think that in gas chromatography, we don't pay enough attention to hard cutting multidimensional GC just because you can use wide bore columns and isolate peaks, right? We've done this in the lab, and you can isolate unknown peaks using a MDGC system. You can use 3 dimensions if you need to, and then you can perform NMR, elemental analysis, and other things like that. So this is just as straightforward as it is with liquid chromatography. So I think just because we're finding so much more peaks in our chromatograms, we're going to have to revisit semi-preparative gas chromatography.
Okay, thank you. Now from Johnson from Country Federal University of Pernambuco. What are the main Orbitrap parameters that directly influence the quality of the analysis?
Hi, Jenson. That is a great question. It's very nice talking to you, man. I think it is a very robust system. We were surprised on how easy it was to operate the Q-Executive system. Mainly MZ range and mass resolving power. We haven't found that much difference when changing the AGC values. from 1 million to 3 million. And the ion time, the inject time. So inject time for 1D GC, we just set it to auto, and it works very well. But for 2D GC, in order to squeeze those 25 spectra per second, you need to define the ion time up to 3 or 5 milliseconds. But I think these are the parameters.
Okay, thank you. We don't have more questions from the chat, but I have two, if I can make. They are simple, but when working with Orbitrap, it tends to favor the O2 class. Is this also happens with these new instruments that you presented here? You said that something like that, one of the presentation, the O2 class was the prevalent one. And we have already observed this in our studies.
It depends. For electron ionization, we don't see that one class is favored over the other. So that is a very interesting feature. But sometimes you don't get the molecular ions, so it's kind of a trade-off. But EI is definitely a way to go. When we move to chemical ionization using methane, we found that straight hydrocarbons and branched hydrocarbons exhibit a much lower response factor compared to compounds that have heteroatoms. So nitrogen-containing, oxygen-containing, sulfur-containing. So we predominantly see the polar compounds in judgment to the straight and branched hydrocarbons. But you can still see them, but obviously there's a very big difference in the response factors. But this is using methane. We're trying to shift to ammonia as the reagent gas, but we don't have any data yet to discuss.
But now that you said, but the working with ammonia is kind of complicated because of the corrosive, and it can prejudice your instrument. And the second question that I would do is, when you are dealing with GC by GC Fourier Transform Orbitrap applied to petroleum, is that is the hydrocarbons, as you said, do you really need high resolution, even from 1500?
Right. So if you're looking at hydrocarbons in particular, but not just hydrocarbons, but if you're looking at a homolog series, if you're able to have a minimum mass resolving power to assign the formula, that's enough, because it doesn't matter if you're going to have 1 million or 15,000 if you're talking between members of a homolog series, because they'll have the same formula. So you need to work on chromatography. So there's definitely you need to improve chromatography for, say, geochemistry biomarkers by GC. If you don't have good chromatography, if you don't have a reliable database, it doesn't really matter how expensive your instrument is.
Okay. The same as I believe it too. So I think that we don't have any more questions. So I'd like to thank you once again for being here and answering our question. And I think that you may be accessible for any other question that people may have. And thank you again. And this is the end. Bye.